Welcome. This video is going to explore the basic features of UML sequence diagrams. Sequence diagrams are a kind of interaction diagram, and that means that they are used to record the interactions between objects, usually, sometimes instances of other classifiers. So suppose that we're interested in the messages that pass between an object of class copy in our library system and an object of class book. So we've chosen a name for our object of class copy, and imaginatively it's C, and similarly a name for our object of class book, which is B. Now the simple kind of sequence diagram we're going to talk about today is just considering a single particular scenario, so that we're not going to consider the different things that might happen depending on the value of a Boolean condition or what have you. You can do that using fragments, which you'll learn about later. We're going to keep it basic for today. This is all about the messages that are received and sent by these objects in some particular scenario. Time flows down the page, and each of our objects is given what's called a lifeline, so that you can easily read off the sequence of messages which each object sends and receives in our scenario. I'm talking about these as objects, by the way, but technically speaking in UML they aren't precisely objects, but for all practical purposes they are. So let's suppose that in the scenario we want to record, something from outside, we'll talk a bit about what later on, is going to send to our copier object a message, borrow, with no arguments. Now this of course only works if an object of class copy is going to understand that message. In other words, if the copy class includes an operation, borrow, which takes no arguments. But let's suppose that that's the case for now. Let's suppose that after thinking for a bit, computing for a bit perhaps, our object of class copy is going to send to some object of class book, the one that we're depicting in this diagram, its message, borrow. It's quite common for different classes in the same system to have operations which have the same or closely related names like this. It can be confusing, but get used to it. You may recall when we looked at the class diagrams, we supposed that our book class had an operation called borrow, which took a copy as an argument, and we supposed that that was to record that some particular copy of this book has just been borrowed. So that's the one that our copy object is sending to book at this point. So it's going to send the message borrow. It has to send a copy as argument. Which copy is it going to send? Well, of course it's going to send itself. And that name C, which we gave to the object there right at the top, can be used anywhere in the diagram to denote the same object. Okay? So our book is presumably going to compute for a bit, and then after a while it's going to send a reply to that message, which is shown using a dashed line and an open arrowhead like that. Okay. The solid arrowhead we've been using shows that these messages we're talking about are ordinary asynchronous messages, so they're the kind that you get in single-threaded systems where the sender is just going to block until it receives a reply. Okay. So now copy has control again. Maybe it's going to do some more computation, and eventually it's going to reply to its message that it got sent. Okay, so that's a sequence diagram. There are several things already to talk about here. Let's first of all think about where this message actually comes from. Now we could just say we're not telling you. Okay, it's going to be what's called a found message. We put a blob on the start of it, and this then is a lost message. That basically just says we've chosen in this diagram to depict part of an interaction. Don't you worry about where this message actually comes from. Sometimes that's the best thing to do. Other times, for example, if you're trying to depict a whole scenario from a use case of your system, you might want to actually represent an instance of an actor on the sequence diagram, and you can do that too. Now let's see if I can drive this tool to get rid of those blobs for the sent and found, and now instead let's draw ourselves an actor. Okay, so This note is going to be an instance of an actor, because the things at the top of lifelines in sequence diagrams are always instances, not classifiers. So let's suppose that it's going to be library member, but it's not going to be the classifier actor library member. It's going to be an instance of library member, let's say L. That's a bit messy, but hopefully you can read that. And that actor too has its lifeline, and then we can just join those messages up to its lifeline, just as though the actor were another object, which in a way it is. And then you've got the question, of course, of, well, what makes it start doing something? Well, you've got to start somewhere. Actors start use cases, start interactions very often. Okay, and notice that you should be able to kind of follow the sequence of what's going on through your sequence diagram. If you find it difficult to do this, you may well have done something wrong. What people quite often do when they make mistakes in sequence diagrams is have messages that sort of spring into existence without anything having prompted the object that sends the message to do so, and that's usually a sign that something's gone wrong. Okay. Sometimes in a sequence diagram it's helpful to show something about which object is actually active at each time, in two senses: which one is actually computing, is actually on a processor, and also which one or ones have received messages that they haven't yet sent, or are in positions where they could do some kind of computation. So let's show you now how to do a bit more, how to show a bit more information. I'm going to rub out these dashed parts of the lifeline and show you how we do something a little more informative. Come back to that in a moment. So what we do is we say from the moment that an object receives a message and all the way down to when it replies to it, it has an it has an activation bar. I think that was the tool trying to be too clever for me there. And the same over here. Okay. So what that shows is, up here, the object is quiescent. It has no reason to do anything. It hasn't received any message. Now it's received a message. That's the sign for it to start computing and do something. And it can continue computing until it sends its reply. Now, because this is a synchronous message, this object cannot in fact compute in there, and so we can make our notation even a wee bit more sophisticated. We can shade in the part of the activity bar where the object is actually able to compute, where it's actually on the processor. This is sometimes helpful because you can then imagine kind of squashing all the lifelines together, and you can see that at any one time there should be one object which is actually computing if they're all objects which are sharing the processor. Actors, however, are different because, of course, you don't control what actors do. That's the whole point of them being actors rather than parts of the system that you're designing. And so, by a reasonable convention, if you're showing activation bars like this, then an actor will have an activation bar that occupies the whole of the interaction that you're representing. And I suppose technically if we were showing shading, we would probably want to shade it all the way down as well. Because the thing about actors is you can't tell when they might do a thing. Because you're not designing them, you don't control them. Ooh, I don't understand this tool. Anyway, you know what I mean, hopefully. Imagine that bar completely shaded. And that is a sequence diagram. A nice basic instance level sequence diagram.